Welcome to Module 3 of the Gould's Water Technology Turbine Pumps e-learning course. This module will cover the criteria and procedures for selecting a line shaft turbine, as well as design options for your consideration based on the type of fluid or well conditions. After completing this module, you should have a better understanding of the information you need to select the proper vertical line shaft pump for any hydraulic application. How long will the column be? How deep is the water level? How much lift is there? These are all unknowns, and they vary from application to application. That's why the standard for the total dynamic head of a vertical turbine pump is not calculated at the discharge head, where it connects to the system piping, but rather at the discharge of the hydraulic component, which is the bowl assembly. Total dynamic head, or TDH, is calculated by adding the column friction loss and field pumping head, which is calculated by adding the discharge pressure and the pumping level. The pumping level is the distance from ground level down to the water while the pump is in operation. You have multiple pump choices to meet your needs. What are some things we need to think about to make the best choice? We need to consider required flow, required head, total dynamic head, maximum horsepower available, minimum pumping level, and net positive suction head available, or NPSH. Net positive suction head, or NPSH, is the pressure needed at the suction of the pump to avoid or prevent cavitation. There are two types of NPSH. The first is net positive suction head required, or NPSH-R. This is the NPSH required by the pump. This number can be found on the bowl curve. The second is net positive suction head available, or NPSH-A. Our NPSH-A must always be greater than the NPSH-R stated on the pump curve. On the pump curve shown, the NPSH-R is 6 feet at 400 gallons per minute. The NPSH-A is calculated using the formula shown here, where NPSH-A equals HA minus HVPA plus or minus HST minus HFS. So what does that mean? HA is the head absolute and equals the absolute pressure in feet of liquid on the surface of the fluid being pumped. Then we subtract HVPA, which is the head vapor pressure. It equals the head in feet corresponding to the vapor pressure of the liquid being pumped. This information can be found on standard industry charts for properties of fluids at various temperatures. Next, we either add in or subtract HST, or head static. It equals the static height in feet that the liquid supply level is above or below the pump center line, or impeller eye. And finally, we subtract HFS, which is head suction friction loss. It equals all suction losses in feet, including entrance losses and friction losses through pipe, valves, fittings, etc. Typically for vertical turbines, this equals 0, unless a tailpipe or something else is connected to the inlet of the pump. Now, let's apply this formula to a real-life scenario. In our example, we have determined that the atmospheric pressure equals 34 feet for a vertical turbine in an open tank. Then, based on the industry chart, we see that our vapor pressure of water is 0.839. Next, we know we need to either add in or subtract HST. In our example, the pump is submerged in the liquid. There is 10 feet of liquid between the supply level and the impeller eye. So, for our equation, we add an HST of 10 feet. Finally, we have to subtract our friction loss. Because we do not have anything connected to the pump inlet, our HFS is equal to 0. So, 34 feet minus 0.839 feet plus 10 feet minus 0 gives us an NPSH-A of 43 feet. And for our example, an NPSH-A of 43 feet is sufficient to cover our pump needs of 6 feet. The formation of vortexes between the pump suction intake and the suction tank fluid surface causes air to enter the pump suction. This mixture of air and water reduces the pump capacity. The formation of such vortexes must therefore be avoided. There is a relationship between the intake velocity at the suction intake and the submergence, or S, of the intake. Minimum submergence is based on 2 times the bell distance between pump center lines and other ideal flow conditions. Refer to the latest HI standard on intake design or consult the factory for more information regarding your installation. Less than ideal conditions will require additional submergence. Make sure that your installation has the appropriate amount of submergence to avoid cavitation. There are several individual choices you must make based on the equations we've already covered and the manufacturer's published data. The first of those decisions is the tentative bowl selection. You want to select the best bowl assembly for capacity and head, pumping conditions, and well size. Curves are drawn per stage, so head per stage must be multiplied by the number of stages required. Add 5 feet of column friction loss per 100 feet of column to the field pumping head to determine the approximate TDH. Choose the best pump, keeping well diameter and engineering limitations in mind. To determine the number of stages required, divide the TDH by the head per stage of the selected turbine bowl. Next, record the efficiency for the number of stages used. Note that, for up to 4 or 5 stages, the efficiency may have to be reduced according to the chart on the right-hand side of the curve. Calculate the laboratory horsepower from the manufacturer's published curve. Lastly, calculate the approximate thrust. First, we obtain hydraulic thrust by multiplying the thrust factor, or K factor from the curve, by the total dynamic head of the pump, and multiplying the result by the specific gravity of the liquid being pumped. The next choice you need to make is the line shaft selection. For this purpose, we are going to reference the Gould's Water Technology Turbine Catalog. Size the line shaft for horsepower under C from the shaft horsepower limitation chart found on page 200.B.01. Next, calculate the total thrust due to line shaft weight using the shaft weights and mechanical friction chart on page 200.B.02. Thrust due to shaft weight equals weight per foot multiplied by the setting in feet. Now, add the thrust due to line shaft weight and the hydraulic or K-factor thrust to determine total thrust. Check that the line shaft will take the thrust load from the horsepower chart on page 200.B.01. Next up is the column selection. Select the column size for the required capacity shown on the column friction loss chart found on page 200.B.04. Choose a column with losses of 3 feet or less per 100 feet of column, unless the setting is very short, making column friction negligible. Now you're ready to make your final bowl selection. Begin by calculating the column friction loss. Multiply the loss per 100 feet by the selected column friction loss number from the chart on page 200.B.04, and then multiply the result by the number of 100-foot lengths. Now, add that number to the field pumping head. This result is the total dynamic head. Finally, reselect the number of stages and head per stage for the new total dynamic head, and calculate the new laboratory horsepower from the manufacturer's published curve. With the new laboratory horsepower number, check that the line shaft you selected can carry the new horsepower, using the shaft horsepower limitation chart on page 200.B.01. Verify the line shaft stretch on page 200.B.07. If the stretch is greater than the lateral adjustment, consult the factory or choose the next larger shaft size using K-factor thrust only. Next, we need to do a brake horsepower calculation by adding laboratory horsepower to the shaft loss and the driver thrust-bearing loss under certain conditions. To calculate the driver thrust-bearing loss, use the following formula: 0.0075 per 100 RPM per 1,000 pounds of thrust. Or, you can calculate the shaft friction loss from the table on page 200.B.02 and multiply that by the number of 100 feet lengths. Add this to your laboratory horsepower to determine the brake horsepower required to power your pump. Select the driver size based on the brake horsepower, speed, and your total thrust calculation, and note the driver's base diameter, or BD. Lastly, you want to select a discharge head for the column size you've chosen and the driver's BD dimension. For settings greater than 1,000 feet or pressures greater than 400 psi, consult the factory. Now, let's go over some of the configuration options that you can consider and why those are important. There are two types of impellers to consider, each with their own advantages and disadvantages. The first is the open impeller. This impeller has two primary advantages. The pump output can be varied by adjusting the impeller position, and it's very good at handling water carrying larger solids. It also has some disadvantages. The impeller lateral adjustment is very critical, needing to be 0.015 or less. Open-type impellers also have no wear rings and are more expensive to repair. Additionally, open impellers create higher downthrust. A closed impeller, on the other hand, creates lower hydraulic downthrust and costs less to repair. What's more, it's not limited by setting depth or the number of stages, and the lateral adjustment of a closed impeller isn't critical like it is with the open type. However, closed impellers come with a cost. Lower pump efficiency and a fixed pump output are the main drawbacks of a closed impeller, along with limited solids handling capabilities. The choice of bearings is important because they support the shaft. There are two main types, rubber and bronze. Rubber bearings are typically used for open line shaft assemblies, with either a threaded or flanged column. Bronze bearings are used in enclosed line shaft assemblies, also with a threaded or flanged column. A third option is non-rubber bearings in an open line shaft assembly. Open line shaft assemblies are used for shallow set applications, usually 100 feet or less. This type of assembly requires a pre-lube system for static water levels exceeding 30 feet. Otherwise, the line shaft bearings are lubricated by the pumpage and the shaft sections are joined by threaded couplings. Closed line shaft assemblies are used for deep set applications, usually over 100 feet in length. This type of assembly is oil lubricated and is used in applications where the line shaft and bearings need protection and proper lubrication. Water-flushed line shaft bearings are available for pumps that have abrasive materials flowing through them. The rigid flanged coupling is used to couple the pump to a vertical hollow shaft driver. The impeller adjustment is performed using the nut located on top of the motor. The adjustable coupling is designed for vertical solid shaft drivers. With this type of coupling, impeller adjustments are made by using the adjustable plate in the coupling. An adjustable spacer coupling has the same function as the adjustable coupling, but with the addition of a spacer. The spacer may be removed for mechanical seal maintenance without disturbing the driver. Different applications can require different materials of construction and configurations. Cast iron, ductile iron, stainless steel, nickel aluminum bronze, hardened bearings and shaft, and varying types of sealing assemblies. Cone strainers are used in well applications to keep large objects out of the bowl assembly. Manufactured using a wire-wrapped construction, they're made of galvanized steel or 316 stainless steel. Basket strainers are used in sump applications to keep large objects out of the bowl assembly. They're designed with a low profile for deeper settings in a sump and manufactured of galvanized steel or 300 series stainless steel. The packed box is the most economical sealing method for open line shaft pumps in relatively low pressure applications. These use acrylic yarn and graphite packing. An optional shaft sleeve is available. The water flush tube connection is supplied when pressurized water is introduced into the enclosing tube for bearing protection against abrasive surfaces. Oil lubrication is recommended when the water elevation would cause the upper line shaft bearings to run without lubrication during startup. Oil is fed through a tapped opening and moves down the enclosing tube, lubricating the bearings. A single seal is a popular sealing method for low to medium pressure applications. Its cartridge style makes installation and maintenance easy. A dual seal is 2 seals mounted in line. The chamber between the seals can be filled with a buffer liquid and may be fitted with a pressure-sensitive annunciator for safety. There are several coating options to consider based on your application. Whether you're pumping potable water, seawater, or river water with abrasives, these sealing options can protect the fluid from contamination and shield your pump. For potable water or drinking water, where no odor or contamination is allowed, such as in the food processing industry, the coatings recommended should be certified by NSF International in accordance with ANSI NSF Standard 61. Tnemec 140 is an epoxy applied at 4 to 6 mils per coat. It has a total minimum thickness of 8 mils for Type 1 and 20 mils for Type 3. Maximum service temperature for this coating is 130 degrees Fahrenheit. This coating is used in potable water applications and is certified by NSF International in accordance with ANSI NSF Standard 61. Type 4 Scotch Coat 134 is a fusion-banded power epoxy. It's applied at 10 to 12 mils with a maximum service temperature of 160 degrees Fahrenheit. This coating is used for potable water, seawater, brackish, brine, and river water with abrasives, and is certified by NSF International in accordance with ANSI NSF Standard 61. Type 1 Carboline Bitumastic 300M is a coal tar epoxy applied at 9 mils per coat with a maximum 18 mils. It has a maximum service temperature of 120 degrees Fahrenheit. This is best used for seawater, brackish, brine, and river water with abrasives. Type 1 and 3 N-Guard 460 is an epoxy applied at 10 mils per coat with a maximum 20 mils. It has a maximum service temperature of 140 degrees Fahrenheit. This is best used for seawater, brackish, brine, and river water with abrasives. Type 2 Carbozinc 11 is a coating of inorganic zinc applied at 2 to 3 mils per coat. This coating is not to be used when acid or alkali solutions are present, unless it has a suitable top coat. The maximum service temperature is 200 degrees Fahrenheit. This is best used for seawater, brackish, and brine water applications.